Hi, my name is Tom and you are at level 19 out of 30 easy steps to learn everything about Einstein's special relativity. I'm assuming you've seen some of my previous levels. So, GP, hit it! Hendrik Antoon Lorentz. He's Dutch, that's why I'm pronouncing his name in Dutch. Hendrik Antoon Lorentz. And this level is divided in two parts. Level A, well, section number A, which is for all, which is this part, it's just a story, so don't be afraid, there will be no formulas, no math involved, and in a separate video we will do a little bit more deep dive for the daredevils. And as you may have seen in previous levels, sometimes I go another step deeper and then we are truly going to rock climb. But for Hendrik, we are not going to do rock climbing. We're just going to do level A and level B. So let's get into it. Oh yeah, and level B will be about the Lorentz transformation in math. But you can forget about it. Let's first meet Hendrik Antoon Lorentz and, well, maybe first start what it was all about. In levels 5, 13 and 18, we've talked about the Galilean transformations, which is just everyday relativity. I'm going to slowly recap it. We assume we have some event E, which could be a light flash, something moving, and there is an observer and he writes down, I saw this happening there and there at this time. Then there's another observer who might be moving with a constant velocity relative to the first observer, and he also writes down, I saw the same event, but I saw it at a different location at a different time maybe. That goes into the Galilean transformation box. The differences between the two observers go in, and in Einstein's world, as I have told in previous levels, the only difference is that the observers move rectangular with a different velocity, so they have a velocity relative to each other. That goes in there, and the box will tell us what observer 2 is seeing. And that's all there is to it. And I think even in level 5 we already derived the equations for Galilean relativity or the Galilean transformations. But trouble. We've seen in, I think, level number 17, there's a lot of trouble, especially with light. So let's look at the trouble with light. Here I have a setup. There's a track, and on the left there is an old-fashioned train with a cannon. And the cannon has a bullet in it, and it will fire the bullet at the other train on the right, the red train. And this is what I call the observer. And the observer is going to look at the bullet. Or, well, maybe it's a tennis ball, something like that. But let's first see the world, because, you know, I make my own animations and therefore I can spin it or do this. Whoa. Really cool models. Not mine, I have to say. Credits are in the text below. So this is the cannon, and this cannon is going to fire. First, you have to remember, if you didn't see in previous levels, we're not going to do a lot of math. We're not going to do really math, you know. But you do have to understand that if an observer writes down the coordinate x of some event, we write x and then the event, comma, from which perspective. In this case, you will always know who's talking about what. We do the same for time and we do the same for velocity. So here we go. It will make sense if you see the example. Here we have the train with the loaded cannon and the observer. And the cannon, or the train with the cannon, will start driving 10 meters per second to the right when I start the animation. The cannon, the ball coming from the cannon, the bullet, will leave the cannon with a relative speed, relative to the cannon, with 20 meters per second. So if you were the cannon, you would see the bullet go outwards 20 meters each second. And the observer will move to the left, that's why there's a minus sign, and in this case, he will go 30 meters per second. Okay, so far so good. Let's see the animation. I put an arrow where the ball is because it might be too small on your screen. The interesting thing is, what would be the speed of the ball relative to the ground? Well, you know it's relative to the cannon, it's already 20, and the cannon itself is relative to the ground 10. So if you add them together, 10 and 20, you get 30 meters per second. So the ball or the cannon, the bullet, is flying at a velocity of 30 meters per second relative to the ground. And now the next question will be, how fast is the ball going relative to the observer? Try to do the math. It's not that difficult. I'm going to tell the answer now. It's 60, right? Because we add another 30. The observer is running towards the ball with a velocity of 30 meters per second. So if you would not have any reference point and the observer would think, I'm not moving, I'm just, everything around me is moving, but I'm not moving, then he sees the ball coming at him at 60 meters per second. So far so good. Now let's do the same experiment, but instead of a cannon shooting a ball, we have a loudspeaker shooting out a sound wave. A blue speaker is on the train, mounted, and a sound wave is going away to the right. And a sound wave is nothing more than a pressure wave through the air. So I try to draw the compressed air molecules at different intervals. Because sound is a wave, we have to talk about its medium. We have seen in previous levels, when you talk about waves, we have a medium, and the velocity of a wave is, well, you always need to define it relative to its medium before you do it relative to other stuff. And in this case, we will say that the air, which is the medium of the sound, is at rest with the ground, at rest with the track. So the train on the left will do the same as the one in the first experiment. It will move 10 meters per second to the right. But instead of that, we say the speaker relative to the ground, we say the speaker relative to air, which is the same in this case. And also the observer train, its velocity is minus 30 meters per second relative to the air, which is also the same as relative to the ground. But the reason we chose air is because when we talk about the speed of sound, we are actually talking about the velocity of sound relative to the air, its medium. And in air, it's around 343 meters per second. It can be a little bit different based on temperature and pressures, but this is the basic number. Now let's do the animation. So what we see is that both trains do the same as in the first experiment, but the sound wave doesn't behave like the ball, the cannonball. It doesn't seem to be affected by the fact that the speaker is moving. And that's true, The sound wave cares about air. And if the air is not moving, then it's just moving relative to the air, which is the same as relative to the ground. But the speaker, from the speaker perspective, you are catching up on the wave. So you're catching up 10 meters each second. So that's why the velocity, that's why there's a V, velocity of sound from the perspective of the speaker is not 343, it's 333, right? The other one, the observer, is running towards the sound, and there we need to add the velocity of that observer, which was 30, and if you add 30 to 343, you get 373. So this is the same experiment for sound. Now let's do this for light. Are you ready? There is now a flashlight mounted on the train instead of a speaker or a cannon, and it has a short flash. And all the stuff is the same. I picked ground now as a reference point, and that's because light, although it's a wave, we've seen that in previous levels, it doesn't seem to have a medium. At least we haven't found it yet. And if we find it, we have a major problem. But that's I'm way ahead of myself. So I took the ground as a reference point. So the light moves relative to the ground at, a huge number. You can see it there. Now we do the animation, and I can tell you there is a lot wrong with this animation. In fact, I can't even have a single animation which will show you the perspective from the flashlight on the left, together with the perspective from the observer train on the right, together with our perspective as viewers. We are attached to the ground, because we will all witness the velocity of light to be the same. No matter if you are at rest with the ground, running towards the wave, or running with the wave. It does not matter. And this, ladies and gentlemen, is the trouble with light. And it's a huge issue. And I think in level 17, we talked about ether and the Michelson-Morley experiment and the crisis in physics. This is it. This is the crisis moment, and we had to solve it. So Lorentz and some others came to the rescue. Let's see it on the timeline. We talked about almost half of our levels, 1 through 14, on Einstein's mountain dealt with electromagnetism. Here it is. And in 1864, we discovered that light is an electromagnetic wave traveling at a very specific speed. In level 16, we saw that it is a wave, because we did the double slit experiment of Thomas Young. And in level 17, we started looking for the ether, the medium of light. And in 1887, Michelson and Morley did an experiment trying to find this ether, and they failed. Well, they didn't fail, but there doesn't seem to be an ether. And then the mathematicians stepped in. And here is a lot of mathematicians going at it. And I have to use my notes to see, to guide you through this. It will be a little bit, mathematical, but I will make it quick and painless. I will try. So Joseph Louis Field, he came up with switching perspectives, because switching perspective from observer 1 to observer 2 and back is the same as doing a coordinate transformation. And he came up with a set of coordinate transformations called conformal, which means if observer 1 sees a ball, observer 2 also sees a ball. Then in 1871, I'm going to skip one, Sophus Lie, or Lieu, I'm not sure how to pronounce it. He made it from a three-dimensional ball to an n-dimensional ball. So if you have the ability to see a six-dimensional ball, another observer will also see a six-dimensional ball. Ribacourt and Laguerre, they added something. I think they added the planes, right? Yeah, they made sure that balls will be balls, but planes, and I don't mean an airplane, I mean a flat surface, will also stay a flat surface between two different observers. So that's good. It's really convenient in physics that planes stay planes. Then Woldemar Voigt, what he did was he added the thing that waves kept waves if you switch perspective. So now we have balls keep being balls, or spheres are still spheres, planes are still planes, waves are still waves. Then Fitzgerald and Lorentz come up with something called contraction, which I will deal with in level 27, so I'm going to skip it for now. And then in 1892, Lorentz is formulating his own theory about the ether, the medium of light, and why Michelson and Morley were unable to detect it. And you see there is, it's 87, and he came in 92. So it took them 5 years to come up with a theory to explain the results of Michelson-Morley. But still there was ether in Lorentz's mind. 1895, he had the theorem of corresponding states. It's a little bit fuzzy, that one, so I'm going to skip it. It's about a hypothetical, reality in which you see the same things as real reality. I'm going to fast forward to 1899, again another 4 years later, and then Lorentz came up with a transformation, a way of switching perspective that almost almost solved the trouble with light. And you have to understand the trouble with light is the same as the trouble with Maxwell's equations. If you haven't seen the first 14 levels, Maxwell's equations describe electromagnetic waves, and light is just one of them. And then in 1904, another 5 years later, he's almost there. He can show that, almost for all speeds it's invariant, as they say. Poincaré, in 1905, he dotted the I. I have to look at my notes. He published a paper called Sur la dynamique de l'électron, or the dynamics of the electron, or the rendiconti del circolo matematico di Palermo paper. And he labeled it the Lorentz transformations. Basically what he did, he took it, he simplified it, and he dotted the I. And there we have it. Now we have a mathematical model, which we will not show at this level, don't worry, no math, but a way of switching perspective that deals, that's fit for the example with the ball that we saw, the cannon. It's fit for sound waves, but it's also fit for light waves. So, hooray! Hendrik Antoon Lorentz. And he's Dutch, and I'm Dutch. And these are not my words, but one of my friends, Sander, he says, Tom, if it ain't Dutch, it ain't much. And he is living not even in the Netherlands, he moved outside of the Netherlands. Hendrik Antoon Lorentz, he's because I'm Dutch, he's our first Nobel Prize winner in 1902. He was born in a city called Arnhem. And Arnhem is a great city to be born in, and I can tell because I was born in Arnhem. So I have already two things in common with Hendrik. Here he is. He is ranked, as you've seen in the previous levels, I'm ranking the stars. I took some ranking, there are several, I picked one. And in this ranking he's ranked at number 84 of the greatest scientists ever lived. And I think that it's not fair. He should be higher up in the chart. He's Dutch, of course, but I don't want to make this a Dutch thing, right? I mean, science is science, it has nothing to do with the country where the scientist came from. So let's just drop the fact that he's Dutch, right? And that I'm Dutch. Einstein on our Hendrik. He says the enormous significance of his work consisted therein that it forms the basis for the theory of atoms and, now it comes, for the general and special theories of relativity. The special theory, and Einstein means his own, was a more detailed expose of those concepts. So he gives full credit to Lorentz solving it, and he said only what I did is I detailed it. For me personally, he meant more than all the others I have met on my life's journey. So, yeah, you. Of course, I'm proud because he's Dutch, but I will drop it now. But I don't think it deserves to be at number 84. He should be a little bit more higher in the ranks. Then Poincaré, also at number 28, out of the 100 greatest scientists ever lived. He says it's the most satisfactory theory is that of Lorentz, and he credits Lorentz for his work. So yeah, Hendrik Antoon Lorentz. And basically what Hendrik did was, if we take a look again at the picture of Galilean relativity, where we had an event, two observers writing down notes like the location and the time of the event, and you put it in the magic box where there's some mathematical formulas. Instead of the Galilean transformation, now we do the Lorentz transformation. It also needs the difference between the two observers, which is their velocity, and it will tell you what observer 2 will see. And now this model fits our previous experiments. If you put in the experiment with the cannon and the ball, you get good answers. If you do the sound wave, you get good answers, but also if you do light, you also get good answers. Both observers will always see the speed of light the same, no matter how fast they are running away from it or running towards it. And basically you could say Lorentz transformations is an upgrade of Galilean relativity. This is it for the level 19A, which is for all. If you are curious and you want to have a little bit more in depth, I invite you to watch level number 19B, where we look at the math involved. GP, hit it!